All right, now we're introducing a new thermodynamic potential, and that is enthalpy. So previously we were talking about internal energy, and we're saying that we can talk about enthalpy in that the change in enthalpy is equal to the energy supplied as heat at constant pressure. So before we were talking about processes happening at constant volume, and we were talking about internal energy. Now when we're talking about enthalpy, we're talking about things happening at constant pressure. So we can say that dH, or the infinitesimal of entropy, not entropy, enthalpy, dH, and H is for enthalpy, dH is equal to dQ. And if we're trying to measure this change, then we have delta H is equal to Q with the subscript P denoting that we have something taking place at constant pressure. Okay, and if we're thinking about this in terms like in the expansion work video I drew like a simple diagram of a piston, we can say when a system, and we can just talk about a piston, for example, a simple piston. When a system is subjected to constant pressure and is free to change its volume, a portion of the energy supplied as heat may escape back into the surroundings as work. So in this case, we have that the Q is greater than the change of U, or greater than the change of internal energy. And this is because a portion of this energy is used to do work on the surroundings. And how do we know this? How do we know that if we're heating something, then at constant pressure, that the dH is going to be equal to dQ? Why are we using H instead of U? Okay, so we can start by saying if we have H, which is enthalpy, and then we add some infinitesimal amount of enthalpy dH, then we end up with U is equal to du plus PV plus PdV plus VdP plus the two infinitesimals dP multiplied by dV, which that's just zero because we're multiplying together two infinitesimals. And we also know the definition of enthalpy H is equal to U plus PV. Okay, so we end up with dH is equal to du plus PdV plus VdP. Again, because dP and dV multiplied together, that just equals zero. We also combine U plus PV just into H, and we just write that as H. And we can subtract that from the side of the equation that has H plus DH. And we end up just with DH is equal to DU plus PdV plus VdP, okay? And then we can also say that DU is equal to DQ plus DW, which is the first law. So we can say that DH is equal to dq plus dw from the first law, and then we add that to pdv plus vdp. And if the system only does expansion work and is in mechanical equilibrium with its surroundings at a pressure P, so we're just having constant pressure, we're saying that dw, which is the expansion work, is equal to negative pdv, okay, our expansion work. And so we can subtract the negative PdV from PdV that's already in the equation. That takes out PdV and dW, and we end up with dH is equal to Q plus VdP. But wait, we said that what if heating occurs at constant pressure? So that also gets rid of our term VdP because we don't have any change in pressure. It's constant. So we end up with dH is equal to dq at constant pressure. And that's why we use enthalpy in these situations, and we use internal energy in these to describe or to evaluate these processes that occur at constant volume as opposed to constant pressure.